take a look at number 22. We have a box being pushed against the wall and it's not moving. So typically, if you want to hold something up against a surface, you know that pushing it into the wall will prevent it from moving. And our picture looks like this. Here's our object, and we're pushing it into the wall with some sort of force there. And what's happening is it's not moving. Now that doesn't quite make sense to most people when you start to look at the forces. Here we have an applied force that way acting on the object, and we know that gravity is down. But this force cannot cancel out the force of gravity. Doesn't make any sense. They're not in opposite directions. So what ends up happening is that when you push something into a surface, the surface will push it back the other way. We have a normal force arising like this. And then when the normal force appears, now we're going to get a force of friction upwards. And it's going to be that friction that balances out the gravity. So if you're looking to figure out how to approach a problem like this, we have an object that's not moving, so we know that all forces are balanced. Let's take a look at our x forces. Balanced. That's positive, that's negative. Our applied force is to the right, our normal force is to the left. Guess what? Our applied force and the normal force, they are equal in magnitude. Y direction, that's 0 as well. Let's see, I think the problem asked us what minimum force we need to make this happen. So as you push this in, static friction is present, but if you set the force of friction equal to F of S max, then we'll get that threshold value. And essentially we'll get that minimum force needed for this to happen. Gravity's down, so friction's up, gravity's down. Guess what? These two things are equal as well. So F of S max and FG, they're equal. F of S max, we keep consistently rewriting it as mu S times N. And FG, probably could have wrote that as mg. We'll do that in the next step. What we're going to see is that, hey, in the x direction, we're going to take that information, put it down into there, substitute that in for n. So you get mu s times the applied force is equal to mg. And that's probably enough information for you to solve for your applied force needed to prevent this thing from slipping. Long story short, if you reach that force, it won't slip. Anything above it, it won't slip. But if you do not push with a force above this, it would start to slip because static friction would not be strong enough to hold it in place. So that's kind of a, a different type of friction scenario that you guys aren't quite used to, but hopefully now it makes sense. Looking through the other sheets, you're going to see that we have number 16 is probably a good one to look at. Actually, let's do 14 before 16. If you look at 14, one of the things that we've done a few scenarios with the inclined plane, but this one actually combines kinematics with the inclined plane. So it's a little bit old stuff mixed in with new stuff. You see the boxes starting here, it's ending here. We're told that its velocity is 7.0 meters per second going in, and what we have it doing is actually coming to rest on the surface. So just because you're sliding down a surface doesn't mean you're going to continue to slide down. Maybe it's a high friction surface, so it's entirely possible for it to come to zero, or reach a velocity of 0 after sliding down the friction a certain distance. So ultimately, what we would do is, that's labeled D on the figure, but I would probably call that delta x, because that's in the x direction. And you have VI, this is VF, delta x, and we can run through this and start to analyze the entire scenario using a combination of kinematics and also forces. So if we look at the forces aspect of it, we're seeing that, well, it's moving down the incline, so the force of kinetic friction would be that way. There's gravity, there's normal force. There's our three forces, and we have them in raw form right now. I want my gravity in the components, so let's turn gravity into FGX, FGY. Let's leave FK alone, let's leave N alone. There is our figure there. Now keep in mind, this thing's going to come to rest, so it's going to be decelerating. Y forces are balanced. No motion in the Y direction. Remember, the Y direction is this, perpendicular to the surface. So you get same thing that we saw before. N and FGY. Those two things balance out. Again, N equals FGY, and FGY is always mg cosine theta. That's going to be important because we have friction in play here. X direction. I know there's deceleration. Let's write sigma F equals ma. You have two forces basically working against each other. You got this and this. And guess what? This one's winning out now. That's present, but it's not larger than that. It can't be. Remember, this is the positive direction here. This is the negative direction. So I'm going to call that my positive force, that my negative force. I have FGX minus FK. And so FGX can be rewritten as mg sine theta f of k mu kn. And then we take that, put it into there, and look at our expression now. Mg sine theta mu k mg cosine theta. And it turns out the mass of the box, they give it to us, we don't need it. We can get our acceleration. Excuse me, that's supposed to say minus right there. We can get our acceleration, and then once we get our acceleration, you should find that if you did it properly, I believe you're going to get a negative value here based on the numbers provided. And then once you have your value of A, whatever that is, you can go back with your kinematics knowing VI, VF, there's your 3 out of 5 kinematic variables, and you could solve for delta X. Alright, let's do number 16 as well. So if you look at number 16 here, take a look. We are applying a force to B. There's a block A on top of it, and everything's going to move. And essentially what we're asking is, what is the maximum value of force that can be applied before box A slides off box B? So, a few other pieces of information here. This surface is frictionless, so you have no friction here. But in order for this box A to move, we're going to have friction between these two objects. So if we're looking at those, essentially, here's our scenario. Two objects. Here's B, here's the surface, here's A. And what's happening is that we are applying a force to object B only. That's what we're in contact with. Everything moves though. By the way, we're given numbers here. I believe we're told that this is 1 kilogram, this is 4 kilograms. And so if you're looking at free body diagram acting on object A, well, let's keep track of everything. I've got a force of gravity. Let's call it mass of A times G. I've got a normal force acting on it. Let's call this the normal force. I'm just going to label it N now. We're going to modify it in a little bit. You'll see why. And in order for this thing to move forward, there has to be a frictional force as well. So I'm going to call that, let's call it F of S max, because essentially they said we want to know how hard we can push it before it slips. So we'll find that threshold. So there's our forces acting on object A right now. Let's look at object B. Remember, I always like to draw my force diagrams away from the original picture. If I'm trying to do all these arrows on top of this, it's just going to be a soup of arrows all over the place. And we might get confused. So let's call this force of gravity MBG. There's a normal force. Now, here's why I want to not label each of these N. These things are not the same here. Let's say what's applying the normal force. The normal force here comes from the floor. Let's call it F on B. Normal force F on B. This one, let's call this normal force B on A. We know that we're applying a force here forward. And that's just labeled F. And we got to be careful here, Because essentially, let's not even look at object B just yet. Let's look at object A. Essentially, if we're trying to figure things out here, we can analyze object A on its own. So, here's the work for object A. Y forces I expect to cancel out. No movement in the Y direction, only the X direction. So normal force B on A, that's up. Gravity down. Guess what? They're equal to each other. So the normal force of B on A is equal to mass of A times G. And you know what? We actually know what that is, since mass of A is 1 kilogram and G is 9.81. We get 9.81 newtons is the normal force acting on this object. So we know that that's 9.81. We know that that's 9.81. That's probably useful information. No, we're not doing mass B yet. Sigma F in the X direction. I know we're gonna get it to move, but essentially we want to calculate, a threshold value. What's the maximum acceleration that we can have here? So, what we're gonna do is we're gonna just say, okay, yeah, this thing accelerates to the right. Let's call this mass of A times acceleration A, and then take a look. Our only horizontal force is this, F of S max. Well, we can rewrite F of S max as mu S times N. Remember, that's NB on A. And so, we can be more specific here. The normal force is actually equal to the mass of A times G. It's equal to the gravity there. So when we want our acceleration, it's going to be that, mu S times G. And I think we're told that this mu value over here is 0.5 in the problem. So we can now solve for A here. It'd be 0.5 times 9.81. I'm going to get 4.905 meters per second squared here. Now that's important, because that's really how fast we can allow it to accelerate. That's the highest rate of acceleration you can have. Anything beyond this, it's going to slip. So that's ultimately going to determine what we're allowed to do here. Now we got to be careful here, because what we want to do is we want to find out what kind of force do we need to apply to B here. Now we're actually not done with this force diagram. You got to be really careful. We have the second law, where there may be action-reaction pairs occurring here. In fact, B pushes A up. So what you're going to expect is that A, being on top of B, is going to push B down as well. So there's a normal force, A on B, present as well. And guess what? If that's 9.81 newtons, that's 9.81 newtons. Not only that, but that actually causes friction between A and B, and it causes friction to act on B. So friction doesn't just have to come from below, it can come from above too. And essentially, A is pushing down on B, and it's going to work against this force here. There's going to be a force of friction there as well. And the reason that happens is because if we look at this force here, this is the maximum force of static friction that B is exerting on A. Let's call this B on A. You're going to see another F of S max from A on B. These are an action-reaction pair as well. So essentially, what we're going to have happening is there's going to be a forward force here and a reverse force that are equal to each other. So, a few things. I think we're given this force here. No, we're not. We want to figure out what it is, but we can figure out this force, which means we can figure out this force. So let's just go back to this expression right here. If I just plug in 1 here, and I know my acceleration is 4.905, what I get is that's a 4.905 Newton force. So if I'm looking at the forces acting on B, essentially we'll know the reverse force. So we got our forces acting on B. That has to be 4.905 newtons, because we have just determined that that is 4.905 newtons. And then you have a forward force here, F. Now, I'm not really going to worry about these vertical forces here. They're going to cancel each other out. Let's analyze the x direction here. Sigma F in the x direction equals mass of B times acceleration. There's your forward force. There's your reverse force. And essentially, we have already determined that if we accelerate at this rate, it slips. So that's going to determine how hard we can pull here. We're going to say, we're going to allow you to accelerate at 4.905. The mass of B is 4. The acceleration is A. The force is unknown, 4.905. But A, we have just determined to be 4.905 meters per second squared. So now we can probably solve for F. And if this was all done correctly, it'll match up with the answer that's on the answer key.